guys, in this lesson we are going to understand some rules of ladder language programming. Firstly, we are going to define a project, and while doing the project some rules of branches, networks and crossing will be explained, and finally we'll have a summary. Before we get started with today's video, I just want to inform you about all the great content I have been releasing on the PLC Goods YouTube channel, which includes topics related to industrial automation, PLC programming, HMI and microcontroller based developments and projects. My name is Saeed Reza Fattahzadeh, and if you enjoy this video, I would appreciate it if you could click the subscribe button as well as the notification bell to receive the latest and greatest content I will be posting through the channel. Please be informed that by clicking on the join button and paying a small monthly fee for as long as you want to continue, you can become a channel member to get access to cool perks such as to have access to my exclusive videos, WhatsApp support number, and access to PLC control program codes existing in my YouTube channel. I will add more or edit these in the future and do my best to not to disappoint you and create these hard-hitting tutorials and content that you all like, but I am still growing and I am expanding the channel as well. At the end of the day, I still appreciate your support and consideration. To define our project, see this simple industrial circuit in EKTs, which is a software to test and simulate simple industrial circuits. This circuit has two parts, control and power. Based on these four switches, the control circuit will turn on this lamp and the three-phase motor. Let's test it. If this one switch is pressed, the voltage will reach the lamp and it turns it on. Similarly, when S2 or S3 switches are pressed, the K1 contactor is powered and then it makes the three-phase motor to turn on. Pay attention, this control circuit can turn the lamp on, but it does not have enough power to start the three-phase motor. So this contactor or relay with its contacts is used. Also, when S4 is pressed, S1, S2 or S3 switch can turn both outputs on. Now see this schematic of the PLC wiring circuit in ePlan software. A PLC is used in the control circuit. My PLC is CPU 1200C of Siemens company with this article number. As you can see in this model, it needs a 24-volt DC power supply. At this circuit, there are four switches to control two outputs, and also we have those four switches here which are connected to the PLC. This circuit has a lamp and a three-phase motor which is connected to the control circuit with the K1 contactor. Let me move this window. Both of these circuits have a lamp and a three-phase motor which is connected to a control circuit with the K1 contactor. Let me move this window again to show an advantage of the PLC circuits. See the wirings of these four switches. As you can see, the wiring on the left side is a little more complex than on the right side one. So the advantage of the use of PLC is their simplicity in wiring, which makes their maintenance and diagnostic easier in the future. Okay, to briefly explain, our project is to program our PLC with the TIA to turn on the two outputs, a lamp and a three-phase motor based on the right side control circuit logic. To start generating the program, we need to click on Create New Project and then write a name for our project. Well, if you want, you can change this path address which the project will be stored at. If you have more than one version of TIA on your computer, then here select one of them. I have just installed version 16 of the TIA software. Then write your name as a PLC programmer and then you can insert extra information about your project here. Finally, click here to create a project. Then click on Configure a device to define your PLC's hardware in the TIA. Here is empty because we haven't defined any devices yet. Click on Add New Device. Now you see three types of devices. Click on Controllers and find your controller. Mine is CPU 1212C. Then if there is more than one, we must check the article number. This is my CPU article number behind this door or on its right side. If you don't have any PLC, don't worry, PLC programs can be tested by the TIA simulator. So you can select any type of controller as you want. Now click on the Add icon. Now my CPU has been defined in the TIA. If there is another module besides your CPU, you can find it here and insert it into the project. Well, this is the default name of the PLC. So here under the PLC name, after device configuration, in the program blocks folder, click on the OB1 block. OB1 is the main organization block to start programming and call up other programmed blocks. The default language for the programming is ladder. It can be changed. Here you can select function block or ladder language for programming. Now select LAD choice. As you can see, in ladder language, we have a line here on the left side which is called the power line. To have this logic in TIA, it just needs to determine when our outputs are on. When turning on conditions are not true, our outputs remain off automatically. First, I need to insert two coil or assignment instructions corresponding to the two outputs, the lamp and the three-phase motor. To add the second output, I need to create a branch. Now the question is, what address must be written here? Let me show my PLC wiring again. See here, the lamp is connected to the PLC output with this address, Q0.1. So I must write the Q0.1 address here. For the second coil, my K1 contactor or relay is connected to the PLC output with the Q0.0 address. So I write it here. Now right-click on the outputs and select Rename Tag. Here you can choose an appropriate tag or name for the addresses or write your comments. For the Q0.1 address, I write H1 as its tag and signal lamp as its comment. For another coil, I write K1 as its tag, and in the comment part I write the contactor of the three-phase motor. Pay attention to this point. The CPU just understands addresses, so tags or comments just help us to understand the program, and it is not necessary to define them in the program, but I recommend you to do so. Now we need to define the conditions that cause these outputs to turn on. The first condition for the lamp is when the S1 switch is pressed. So let's insert a normally open contact here. Now which address must I write here? Let me show the PLC wiring. The S1 switch is connected to the PLC input with this address I0.0. So I write I0.0 here and choose S1 as its tag. Let's see what we are going to do. These are the three conditions that make the lamp turn on, and there are the ladder programming that we are going to write. In ladder language, there is a power line on the left side, and based on some conditions, the power can reach output and turns it on. Until now, we have just written the first condition in the TIA. Another condition is when S2 and S4 switches are pressed simultaneously. Well, inside the program, we need to insert a branch. Select this place and then click on this icon to open a branch. In this line, we need two normally open contacts, and then with this icon, close the opened branch. See the PLC wiring again. The S2 and S4 switches are connected to the I0.1 and I0.3 addresses of the PLC inputs. So I need to write these addresses and change their tags to S2 and S4. Also, here is a better way to insert addresses. Come back to our defined PLC with a click on this tab or click on the device configuration. Let's magnify the PLC. Here we see H1, K1 and S1 and S2 tags which we have defined before, and the other PLC inputs and outputs which I have not used till now. As you see here, the S4 switch is connected to the fourth input with the I0.3 address. So to use this address, as you can see, we can select, drag and drop it in my program. When I change its tag to S4, its tag on PLC will be changed as well. Now the third condition is when S3 and S4 switches are pressed simultaneously. Same as the previous branch, insert the last condition. See here, I can close this branch manually. I have to use the PLC input with the I0.3 address, which is connected to the S4 switch. After we have defined a tag, we can use the defined tag instead of the address. Here I have defined the I0.3 address with the S4 tag. So another way to insert an address is to write its tag. Let's now define the S3 tag for this address. Here we can see the tags that we have defined them before, and we know which inputs or outputs are not used yet. Now let's see how a PLC works. These three branches are related to the three conditions which turn the lamp on when they are satisfied. If any of these conditions is true, the virtual power will reach the Q0.1 output with the H1 tag in our program. After that, the CPU activates Q0.1, which causes a 24-volt DC to reach the lamp to turn it on. Remember, we wrote the three top conditions in this ladder program, and we have seen how branches can be inserted. With branches, we can make a parallel logic. On the other side, there is the AND logic. It is when a ladder component is inserted in series like S3 and S4 contacts, or like S2 and S4, because if S3 and S4 switches are pressed simultaneously, the power will pass through the branch. In the ladder language, branches are opened downwards after a selected element and are terminated after the selected ladder element. Let's get back to the program by pressing the Ctrl+Z keys on the keyboard. Now let me delete this. As you can see, I can close branches manually, and if you want to delete a branch, all elements of that branch must be deleted. Next, we are going to write an appropriate program for the three-phase motor. You can see here, there are three conditions to turn the motor on. Now let's write its program, which is similar to the lamp program. Okay, we just need to write some appropriate tags because we have defined our addresses already. Okay, our program is complete. Let me have a better view of the program. As you can see, there are two circuits which are called rungs. A rung starts with a power line and is closed by a coil or a box, which is the result of a logic operation that will be written there. Now these two rungs are in the same network with this name. Suppose you want to have a blinking lamp when a three-phase motor is turned on. In this case, both of those outputs can be in the same network. But in our project, the lamp and the three-phase motor are independent. So I move the second rung to the next network. As you can see, the name of the network 2 is changed to the contactor of the three-phase motor. If you remember, this is our output comment, which has been defined for the K1 output. Now let's see what these icons can do. With these icons, we can choose what information to appear in a program: addresses, tags, or comments. Let's talk about the next concept: crossings and nodes. For example, this is a crossing. So a crossing is a node where one branch is closed and at the same time another branch is opened. I press Ctrl plus Z on my keyboard to get back. Now we are going to test this program. If PLC Sim of the TIA has been installed on your computer, you can test the program without any PLC. To test the program, click on the online menu, then select Simulation and click on Start. Then click on OK. This message warns you that starting simulation will disable all other online interfaces. Click on OK. Now you can see your virtual PLC is connected to TIA on the left side. Now it starts checking and compiling the program. Then click on the load icon to move the programs to the virtual PLC. This message tells us the loading is complete without any error. Then here click on Start Module to start the PLC. Pay attention, there is not any hardware switch on the CPU to execute the program manually, unlike S7-1200 or S7-1200 models. Now the ladder program from my computer has been transferred to the virtual PLC on the left. To see what is happening in the virtual PLC program, click on this glasses icon. When I press this icon, we notice that the PLC program is connected to the TIA. As you can see, the working windows changed a little. As an example, the color of this window is changed to orange. To turn on the output, the virtual power should reach the output through one of the three branches. As an example, consider the first line. We want to change the state of the normally open contact of the I0.0 to close. To do this, we should press the S1 switch to pass the 24-volt DC to the PLC input with I0.0 address, but our PLC is virtual. It is not real. So we should change the state of the PLC input in a different way. Here under the watch and force table, click on the force table option. First select any address you want. I select S1 with I0.0 address, and here I write a valid value. For a binary address like I0.0, we just have two valid values, a 0 or a 1, false or true. I write a 1 here and then click on this icon to insert that into the program. As you can see, the main LED is changed to an orange to indicate that maintenance processes mode is activated. As you can see, when an address gets a value from the force table, the F letter appears. In all ladder program, power has reached the output via the first line and the output is turned on. But here, the virtual power just passes the first contact and hasn't reached this output. So let me change the state value of the I0.3 address, which its tag is S4 in the force table. Now, both outputs are turned on. To cancel force values, get back to this table and click on this icon. As you can see, the main LED is turned off. And in the program, our addresses have their real values. After testing, click on the glasses icon to exit from the online mode. Also, we can compile or download programs to the PLC manually. Click here to compile your program. The result is shown here. Now select your PLC and click on this icon to download the PLC programs and their settings to a virtual or real PLC. Pay close attention. The result of your action is always shown here. Similarly, let me test this program with my PLC. So here I have to close the virtual PLC, otherwise the TIA won't find the connected PLC. Again, TIA needs to search IP address of the connected PLC. You can see here that it found the S7-1200 CPU. Let's load the program. This message says the PLC has an incompatible software version. To solve this problem, let's go to the device configuration. Now for the selected PLC, I need to change its version. Also, let's insert the analog module. Again, I select my PLC to load the program and hardware setting. And you can see error is resolved. Click Unload. I select Start Module and then click on Finish. Now let's open the main block and activate the program monitoring. I can turn on or off the output with these connected switches. Let's compare the PLC program with the EKTs circuit. The S3 and S4 switches are pressed and the lamp and motor are on in the EKTs circuit. Similarly, this state is true for the PLC program. Let's turn off the S4 switch in both of them. In this case, based on the EKTs circuit and also the PLC program logic, only the motor stays on. Now, we are going to learn instructions that can be used in programming. We start with common basic operations for both ladder and function block languages. After that, some basic logic will be told, and finally, we will test the XOR logic with a PLC. Remember that we already wrote a ladder program with this PLC wiring. We use these ladder instructions. These three instructions with open and close branches are frequently used in the ladder program. A complete list of all of these instructions is here in the Instruction tab. If you frequently use another instruction, then it can be inserted or removed like this. Also, if you hold the mouse on an instruction, below that, its name will appear, and if you wait for more, a brief comment will be shown, and if you click here, the help window will show a complete explanation of the selected instruction. Now let's start with these three instructions which we used before. Let's see the PLC wiring and the ladder program. As you may know, the ladder programs are similar to industrial circuits, and we can assume that here is the power line, but it's not a real one. Now see the first line. The power can reach here. The question is, how can we change the state of this contact in a PLC program? In PLC programs, each contact has an address which has two states, 0 or 1, true or false. This binary address is I0.0, which refers to this PLC input. In this wiring, the 24-volt DC cannot reach this address, so the state of the I0.0 address is false or 0. And this contact will be in its normally open state. If I press the push button, the 24-volt DC reaches I0.0. Then the state of this contact with the I0.0 address will change to a 1 or true. In consequence, its normal state changes to close. Now, the virtual power can reach this coil with a Q0.0 address. This address refers to the first PLC output, so the PLC changes its state and lets the 24-volt DC turn on the H1 lamp. Briefly, if a 24-volt DC reaches our digital inputs, then the state of the related contacts inside the program change. Let me show the normal status of the first line. Now see the second line. The virtual power can easily reach behind this normally closed contact with the I0.2 address. As you can see in the wiring diagram, the 24-volt DC cannot reach this PLC input unless the S2 push button is pressed. So in the program, the normally closed contact remains closed and the virtual power can reach the output, which turns the second output on. If the S2 push button is pressed, the second output will be off. In the next line, the virtual power can reach the normally open contact. But pay attention to this PLC wiring. In this case, a normally closed push button is used, so the real 24-volt DC can reach the PLC input. So it changes the state of the I0.5 from false to true. In consequence, this normally open contact switches to close and it lets the virtual power reach the output. The last line is similar to the second line, but pay attention, a normally closed push button is used for the last PLC input in the PLC wiring. So the 24-volt DC reaches the PLC input and changes the last contact state to open. So unless we don't press S4, the output will be off, similar to the case in the first line. And although the second and third lines are different, their performance is similar because of different push buttons which are used in the PLC wiring. Now let's see this project which we did it already. Because all the used push buttons were normally open, the ladder program is similar to an industrial control circuit. According to the previous slide, if a normally closed push button is used in a PLC wiring instead of a normally open one, we must change its related contacts to avoid changes in a PLC performance. Okay, now that we know how we can change the state of a normally open or closed contact, we are going to learn this new instruction, Invert RLO. RLO is a short form of result of logic operation. Let's test this program to learn more about this instruction. It seems we have an error in our program. This is my error. The Invert RLO instruction cannot connect directly to a power line. Let's insert a normally closed contact prior to the NOT instruction. These two contacts are normally closed and virtual power will pass through them. Now I click here to compile the program again. Okay, there isn't any error or warning, so I download the program to my PLC. Now let me activate this glasses icon to see my program on the CPU. In ladder language, the RLO is our virtual power, which the NOT instruction inverts its state. As you can see in the first line, the virtual power has reached the NOT instruction. So after that, we don't have it and the output is off. In the second line, the virtual power has not reached to the NOT instruction. So after that, we have virtual power again and this output is on. Note that if we change the sequence of instructions in a ladder language program, the final result can change as well. Alright, like the previous videos, I can test this program with my PLC. Because I have closed the virtual PLC, when I click on download to device, TIA needs to search connected devices to make a new connection. If you click here on the LEDs of the selected PLC, they start flashing. This feature helps us to detect that particular PLC when we have more than one PLC. Let's now load the program. Here I can check the PLC program performance. As you know, I can change the digital input address with the connected switch. I can also change the memory address with a right click on that and then select Modify. As you can see, when I change the connected switch, both PLC outputs are changed as well. Alright, in ladder language, we have this logic. When two or more normally open contacts are placed in series, the virtual power will reach the output if and only if the first and second contacts are closed. In other words, their value changes to true or 1 in a program. This table shows all possible states. The output will be on only when all the contacts are true. And this is the AND instruction in the function block language. Let me write this program in the TIA. This is the AND logic with two contacts in ladder language. Here we can change it to function block language. These are our two contact addresses that have been used in the ladder program. This is the AND instruction in function block language, and this is an assignment instruction that saves the result of our logic. If we need to have this logic with 3 inputs, click here to insert another address such as I0.2. Now I am going to test it. We have learned how to test our programs with the TIA simulator and the force table already. See here, now the first and second inputs are true, but my output is false. Now let me activate the last input. As you see here, only when all inputs are true, the result of an AND logic will be true. Let's exit from the simulation mode and get back to the ladder language. As you can see, this is an AND logic with 3 inputs in the ladder language, in which the contact with the I0.2 address is added here. Now let's learn the next logic. We have OR logic when we have branches in the ladder language. At this logic, if all inputs are false, the output will be 0 or off. In other states, the output will be on. And this is the OR instruction in function block language. The NAND is the next logic. Here are 2 normally closed contacts. In this logic, when both contactors are changed to open, the output will be a 0 or off. This logic is called NAND or not AND because its output is exactly an inverse of the AND logic. The NOR is the next logic. It means not OR, since its logic is exactly an inverse of the OR logic. In this logic, the output will be on only when both contacts are off. Pay attention, OR and NOR logic instructions in the function block are similar, but in the NOR instruction, we have these 2 circles. As an exercise, let's see what XOR logic is. In this logic, the output will be on if and only if one of its inputs is active. Otherwise, the output will be inactive or off. This is XOR logic in ladder. At the bottom, you can see its equivalent program in function block language. Let's compare them. In the first line of the ladder program, S1, which is a normally open contact, and S2, which is a normally closed contact, are arranged in series. So S1 and S2 make an AND logic. As you can see, the inputs of this AND block are S1 and inverted S2. Similarly, the second line in the ladder program and the second AND block are the same thing. As you may know, in ladder language with parallel branches, we have an OR logic. Thus, we have an OR block at the bottom respectively. Finally, both of them store the result of logic or the RLO in H1. It's expected that you can write and test this ladder program. Otherwise, you might need to review the previous videos. Now let's do this exercise in function block language. When we open the OB1 block to start programming, the ladder language is the default one. To change it, right-click here and select the FBD option. Like the ladder language, there are common instructions, and on the right side, we can see an instruction list in function block language. Let me insert 2 AND blocks and define their inputs. Based on the XOR logic, we must use this instruction to invert its inputs. Now let's insert an assignment instruction to store the RLO. If you change the OB1 block language to the ladder, you will see the XOR logic in it. Again, let me change it to FBD. We used some FBD instruction. If you see carefully, here is the XOR instruction in FBD. So let me use this instruction in the next network whose inputs are S1 and S2. Like the previous videos, let's test this program using the force table. As you can see, when I change the S1 and S2 values, the H1 and H2 outputs in both networks are changed similarly. So we can use the XOR instruction directly instead of the first program. Similarly, I can transfer the XOR program to my PLC. Here I will click on Search to find my PLC. The main point is that I have closed the virtual PLC, otherwise TIA won't find the connected PLC. When click here, the selected PLC starts flashing. Let's load the program to the selected PLC. Okay, based on the generated program, we have used XOR logic for both outputs. As you can see, when I change the switches, Q0.0 and Q0.1 are always the same. Well, this is the end of this video. In the next video, we will work on some other basic instructions. Thank you for watching. See you in the next video lesson.